All right, are we streaming? It looks like we might be on. Yeah, cool. All right. Hey, everybody. So a little later than normal. um, my name's Aaron. I'm a data scientist. I'm currently in government. So what I am doing right now is my normal twice weekly study accountability stream. So this is where honestly, it's a little bit boring. So if you just want to chill out and put on some music, I totally understand. What I'm doing is basically going through some lectures to review some stuff that I covered before, and they honestly help me be better at my job and help me understand just, I guess, like things about the world. So I've picked statistics because I've been trying to do applied statistics at my job, where I'm a data scientist. And currently my job doesn't do a whole lot of statistics because I've been doing more machine learning stuff that is mostly like using natural language processing libraries. And I found that I wanted to go back and review some of the basics. And the reason why basics is because I started trying to use like statistical learning, the introduction to statistical learning and the elements of statistical learning textbooks. Those are great, except I felt that they already kind of jumped in with an assumption that you remembered everything about statistics and that you are just wanting to use R with stats. So I decided to go back and look at the underlying theory again, just to make sure that I fully understood what I was kind of like really applying a bunch of stuff to, because I found it's like super easy to maybe inappropriately use some of these libraries and algorithms to situations that don't apply. When I was a chemical engineer, I remember one of the examples that we gave was like in thermodynamics, you can simplify a bunch of equations to known forms, but the issue is that if you use the wrong equations because you forgot what situations called for them, you got the completely wrong answer. So an example would be like if you have an adiabatic reactor where there's like no heat flux going in or out of the system, you can change your second law of thermodynamics and change all of your equations then and then start solving. But if it turns out your reaction is an adiabatic, you've really screwed up a bunch of your equations and you won't get the right answer. So I'm going back to first principles, trying to understand what I'm working with, and basically from there I can more easily apply applied statistics. I just got out of the shower because I went for like a 3-mile run. So I'm still kind of getting that like shower moisture, shower sweat, I guess, where I'm not really sweating. It's just like the shower is affecting me. Anyway, so today I'm still going through this intro stats lecture from Curtis Miller. And it's a class that he taught at University of Utah. So I have shared the overall playlist in the description for the stream, and as well as the video that we're starting with today. I actually saw a little bit earlier today before I took my shower. Was it before? No, I was still working. So I was working, then took a break, studied a little, and then went for that's not true. I was working and then I went for a run, and then I studied a little, took a shower so I could be on camera and be a little presentable. So here I am today, and I am going to start with a video titled QQ plots. If you don't want to study this, it's totally fine. Like, go ahead, and I would say like I do this to be accountable to people. So there's a record of me actually trying to study. And if you want to do something else during this time, that's totally understandable. I think in the future, I'm actually going to be moving these streams to another channel because I find that they're maybe a little distracting. This channel already was kind of split in terms of function.
Some techniques
because it started actually as a photography and travel channel. And then it became more about my life in general, and then I started doing data science stuff
some given
here,
data set.
Which is obviously fun and multifaceted individual, but everyone kind of prefers
appropriate term is
stay in your lane, I guess, on different
probability.
profiles. So my plan is to actually split the streams into a separate channel, and then have the photography be on one channel and the
what you
data
might
science stuff on
hear
another,
as
and then
PP plots.
I have some
This
websites
is a
coming
visual
that will
method
help
used to
make
check
that
whether
more
a data
clear.
set could
But for
plausibly have been
today,
drawn from a particular distribution. There are actually
here we
statistical
are
procedures
actually going through these
null
classes.
hypothesis testing type
So
procedures for
QQ
deciding
plots,
whether
and
a
it
distribution
is
is appropriate for a
chapter
particular data set.
4, section
said, the
6
probability plot
of this
procedure is
book,
quite popular,
and it's
and,
titled probability
it's
plots.
relatively
So
simple.
with that, I'm
You don't
going to
need to use
actually
any,
mute myself so I can
hypothesis testing
maybe
frameworks
focus.
for it.
I should have gotten water.
There
Okay.
are some disadvantages to using the
yeah,
hypothesis
here.
testing approach for deciding whether a data set is appropriate.
Maybe I won't mute myself.
That a visual technique like this doesn't suffer from. It is somewhat is ad hoc the term that I would want to use for distribution. There are actually statistical procedures like null hypothesis testing. This probability percentile plots, what you might hear as PP plots. This is a visual method used to check whether a data set could plausibly have been drawn from a particular distribution. There are actually statistical procedures like null hypothesis testing type procedures for deciding whether a distribution is appropriate for a particular data set. That said, the probability plot procedure is quite popular, and it's relatively simple. You don't need to use any hypothesis testing frameworks for it. There are some disadvantages to using the hypothesis testing approach for deciding whether a data set is appropriate that a visual technique like this doesn't suffer from. It is somewhat is ad hoc the term that I would want to use. I mean, it's not a precise method, since at the end of the day, what you're going to be doing is making some judgment call. But it's also possible that the precision that you get from hypothesis testing is a little false anyway. And just the way that you decide on a distribution in a hypothesis testing framework is a little unsatisfying. Like it kind of operates contrary to how we would advise people practice statistics. So this is a genuinely good method for deciding whether a data set seems to be from a particular distribution. So in essence, what we do is we compare the observed sample percentiles with the percentiles of a data set if it had come from a chosen distribution. And if the relationship between the observed and the theoretical distributions is linear, the distributional assumptions seem reasonable. If there is a nonlinear relationship, then that assumption seems unlikely. And in addition, if you examine very closely the plot, you can probably determine why exactly that distribution is inappropriate for that data set. In essence, what we do is we compare the observed sample percentiles with the percentiles of a data set if it had come from a chosen distribution. And if the relationship between the observed and the theoretical distributions is linear, the distributional assumptions seem reasonable. If there is a nonlinear relationship, then that assumption seems unlikely. And in addition, if you examine very closely the plot, you can probably determine why exactly that distribution is inappropriate for that data set. Now, when we were working in the discrete case, you were able to argue that a certain distribution is appropriate for the phenomena we're trying to model. And I disagree now, after having written these notes, because I wrote these notes a few years ago. I disagree now that it is impossible to develop some arguments for particular continuous distributions, because often certain continuous random variables do have justifications. And there's well, not just justifications, but there is in fact a narrative for many of those distributions as to how they emerge. But at the same time, though, for many physical phenomena, you cannot use that justification. And even then, the continuous distributions are just much more abstract. They don't have these nice combinatorial explanations that the discrete distributions do. So often, if we want to decide what distribution is appropriate for some observed data set, we are obligated to use methods like this. Here is an example of what a probability plot looks like before I keep going. We have, oops, I need to change to a pen. We have a Cartesian plane. And along this Cartesian plane, we have theoretical quantiles along the x-axis. It doesn't matter which is x or y, but I think traditionally it's the x-axis that contains theoretical. So theoretical quantiles. So the theoretical quantiles are the quantiles that you would expect to see if the sample came from some proposed distribution. And for the sample quantiles, so we have the sample quantiles. Oh, come on. Be cooperative. Be cooperative, you stupid computer. Oh, darn it. Okay, sorry, I have to write sideways for this, and my computer doesn't want to cooperate because it's super cheap. All right, sample. So we have sample quantiles. These are the quantiles that we actually observed in the sample. So then we plot a theoretical quantile, like for example the fifth percentile. So we plot the theoretical fifth percentile and the observed fifth percentile. The theoretical 10th percentile and the observed 10th percentile. The theoretical 50th percentile and the observed 50th percentile. All the way through all the percentiles in our sample. And we create a scatter plot of those percentiles. So something looking like this. So here's just for some fictitious data set. And what we hope to see is that the theoretical and the observed percentiles are very close to a line, a straight line. If that is the case, you're never going to actually get an exact line. But if it's the case that the theoretical and observed quantiles are close to a line, it seems reasonable to say that this sample came from this distribution. If this is not the case, then we would probably suggest that, well, it doesn't seem reasonable to say that the theoretical distribution we propose is the distribution for the data set. So this is an example of what we want to see. This is a good PP plot. This suggests that our theoretical distribution is appropriate for the data that we are seeing. Now let's compare that to bad cases. So here are some examples of plots that suggest that the theoretical distribution is not appropriate for the sample. So let's see. We got ourselves a red line. And we could have, for example, the data set has an S shape, although there's a couple different S shapes that we could possibly see. So here's one potential S shape that we could see. Let's create another one. We could have a different looking S shape. And we could see yet a third possibility. Actually, there's a number of possibilities that we could, in fact, see. But here is another possibility where instead of an S shape, we get some U-looking shape. Something like this. Yeah, this could be appropriate. And in fact, reading these plots, we can decide why exactly a proposed theoretical distribution is inappropriate for a data set. So for example, let's consider first this case that I've got in a blue box. Does the undo button work now? Oh, for goodness sakes. Oh, this is ridiculous. Okay, so I don't know why. I think it's my screen. Although, can I...
Well, I totally forgot that I had my window audio out, so you're actually hearing the lecture. So you can probably hear that I am at 1.5x speed. So yeah, if I usually will go back in case I miss something, but he's going through some examples right now. You can probably see on my stream, comparing like good and bad theoretical quantiles, or observed versus theoretical quantiles. And this is a probability percentile plot. Ideally, you want the relationship to be linear, and he's showing like, oh, these are non-linear ones, so they're not good. So the reason why the video is titled QQ plots is because they're quantile plots, and he was calling the percentile probability percentile plots, or PP plots, and then the same thing. So yeah, so a little clarification of terms there. Right now he's showing how to plot a QQ plot in R. I'm starting to think, as a Python user, I'm starting to think if I'm doing stats, I really would just want to use R. I had this thought earlier where like a bunch of these stats lectures I've seen, either from Curtis Miller or from Intro to Stat Learning, Statistical Learning, it's just so much easier to do in R. There's like a function built in already. The way everything's named, I would argue that the functions aren't named in a very explanatory way, but at least everything is like very clear in terms of parameters and arguments for when you try to put things in, and the documentation's there. As opposed to like in Python, if I'm trying to do some of this stuff, like I have to put in different like there's any number of different libraries. I think like most people use scikit-learn, but that's really for machine learning, and pulling a bunch of this data back out is a little bit complicated. I'm figuring out from some of my actual work, and some people use stats models in Python, but like that's not as well documented, and it doesn't always play well with scikit-learn. Yeah, so it's just like, man, maybe Netflix had it right. I think Netflix made Polynote, so that it allows you to mix different languages into the same notebook. I'm thinking I should really pick up more R. So he's explaining he's going to go draw some probability plots by hand right now. So I'm just going to follow along. Oh yeah, behind me are the IKEA barriers that I bought. They should have been here last week, and the bases didn't arrive in time. So it's nice. You don't get to see my bed or my bathroom anymore. It really helps isolate a little bit of the mess that is literally right behind me. And I don't know, I always felt kind of weird that my bed was like, if I stepped out of frame just a little bit, you saw my bed. That was made me feel a little weird. So yeah, now he's describing like, oh, we fit a particular theoretical distribution, a particular exponential distribution onto this observed distribution. But how do we fit like a class in case we don't actually know the parameters? So now he's saying like we have two basic parameters we're trying to fit: the location parameter and the scale parameter for an exponential distribution. So if we just generalize those to a variable, then we can go ahead and figure out how they would potentially affect the distribution. Kind of interesting. He's going through like distributions and their location and scale parameters that basically shape, how you can fit these these QQ plots. And he had a very visceral reaction to, he accidentally put a discrete distribution on there and said, no, we don't talk about discrete distributions in this way. Yeah, so I'm sure that'll show up in the notes at some point. Yeah. So that was the end of the section and the chapter. So that ends most of the discussion around the univariate distribution discussion. So the next chapter is chapter 5. There's a lot of examples in this previous chapter 4. So it would be joint probability distributions, and random samples. So it starts getting a little bit more interesting. So for those who don't know, I do normally work East Coast hours. So I have been up since my body thinks it's 8:45. So let's see, I've been on for about 40 minutes. I think I'll try my best to stream for another 40 minutes and then go grocery shop and get some dinner. Maybe cook today, who knows? And then I will probably call it for the stream. But that means we will be about halfway through the next one. I'm seeing it's like introstats multivariate. Well, I'll just share the link when we get there. We'll be about halfway through that video, and then I'll probably call it for the day. Although I think before we really get into the next video, I'm going to go get some water. The run really took me out today. Yeah. My mouth is open because he said before we end the class. Oh, my mouth was agape because he said before we end the class, I'm going to tell the story of a student came up to me and said, what do you do when you've tried every distribution and the data doesn't seem to fit? And he said, data doesn't have to fit a distribution. You could even just make a new distribution. But he also asked the question I would have asked, which is, are you sure you have tried every single distribution? And he is now showing a paper where there's apparently a walkthrough of a bunch of univariate distributions, and there's so many of them. We only cover like 10, but it's like it's like you can see on the stream here. Let me see if I can. I'll try to show it. Can you? Yeah. So you can see there's like a huge map right now that shows all the different distributions. It's so many. Move back to the bottom. All right. So going back into the lecture. gosh. He just said this isn't even all the distributions. He apparently bought a textbook, and all it contains is a list of like almost every single known distribution, and it's 400 pages long. All right, I'm going to take a quick break to go grab some water and stretch out a little bit. I'll be back in just a second. Okay, and we are back, as you can see, and my mic is on. Cool. All right, so I've got water now, and we're ready to go into multivariate probability. So he's saying we took a huge detour into probability theory, and now we actually get to use those tools in statistics. Big assumption, he said, is from now on he assumes that we've taken multivariable calculus, and he does say which class to take if you haven't taken it. So example 1, x and y are two discrete random variables. So we are going to write out the probability mass function. So it's little p, little p of little x, little y equals big P, big X, little x, big Y equals little y. So he's sorry, I didn't realize my mic was unmuted. I had to readjust my desk lamp. I was getting glare on the monitor. Now I'm, as you can tell, lighting up the nice dust on top of my LCD hood, but not getting glare, so that's good. He's basically writing out, like, when you have this joint probability distribution, what we're trying to do is essentially find the space of an event A happening. So that means that you can consider your random variables as like a tuple or ordered pair. So there should be a space A where a few different of those ordered pairs end up falling into that event space. So he's just like drawing out the diagram for that. So now he's going through a specific example where the x's and y's have actual values, and then trying to find the marginal probabilities of this table. So the marginal mass function, marginal probability function is basically when you fix one variable and you solve for the other ones. That's funny. I was just about to think, like, I took economics and I was like, I don't really like this usage of the term marginal, because like that to me is like, when I learned it before, marginal was like, you know, when you've got a certain amount of whatever, if you wanted to increase by one, like how much would you get for one more unit? And the reason why it's called marginal here is because when you make everything out into a table, you're trying to sum to solve for your fixed value probability function, and you essentially add to the table, and you're writing in the margins of the table is what he said. I was like, oh, okay, all right, that makes sense too. So now that he's actually saying like now that you calculated the marginal distributions, you can actually go and like think about it as like you fixed a value. So it kind of like I heard a little bit of like oh, is this Bayesian? Because it's like given this, what is the probability, right? And you have to renormalize based off of the condition that you've got. And this is now talking about the conditional probability mass function of a y given x. So, hey, sounds, yeah. All right, now he's going to go through an example where fair six-sided die is roll, and the space X, big X, represents the number of pips shown. At the same time, a fair coin is flipped, and Y represents y omega equals 1 if the coin lands heads up, and y omega equals 2 if it lands tails up. So this example is trying to find the joint probability mass function of the spaces x and y, or variables x and y. He is still going through the same examples. Now he's trying to find he already found the marginal distribution, and now finding the conditional distributions and just writing them out. Makes sense. This is an easy case because it's a coin flip. There's only 2 choices, and a die roll. There's only 6 choices. Or actually, the order matters. Just die roll first, then the coin flip. If he were to make this like 2 distinct die rolls, that would obviously open up the space a lot more. Yeah. So right now it works out. It's like uniform and pretty easy. So an important distinction after finding the conditional distributions of p subscript x bar y function x bar y, and then p y bar subscript y bar x function y bar x, is that they're actually different, right? Because this is conditional, so you end up saying like, writing this out, it's like probability of xy over p sub y of y. So you end up with like 1/12 over 1/2, which means it's 1/6. And that's if y is in the space of 1 or 2. And then the other one is 1/12 over 1/6 if x is in the space of 1 through 6. And because they're actually not the same, it means that x and y are independent. That's a big deal. And it kind of makes sense if you think about it, like a die roll and a coin flip, they should obviously be independent. But if you end up in a situation where you can't as easily conceptualize it, like that, I feel like is a good check to see, hey, these are not the same. So that means they should be independent. And that's obviously very good for the statistics and probability stuff that we've learned. Now he's going through creating this in R, creating this table, and calculating the probabilities and the outcomes. All right, next example, basically the same thing, except instead of being discrete random variables, like with the coin flip, it is now continuous random variables. So now, as before, instead of going with a probability mass function, now we work with joint probability density functions. So everything mass becomes density. So let's write that down. Say x and y are continuous random variables. Yeah, I had to mute. I had a little bit of a burp. Sorry about that. Okay, so much the same. Mass functions go to density functions. and he's going through a second example, is bags of mixed nuts, and he's about to write down the joint PDF for the almonds and cashews, and then the peanuts, because that has to be the remainder, is like actually determined by just X and Y. Yeah, so I'm going to go through a little bit of the setup. Actually, let's see. The rest of it is writing out integrals and stuff. So I think actually this is a good time to stop, because it's been about an hour and 26 minutes. And it's 6:30. So it's good time for me to go get some groceries and stuff. Costco might be closing soon. So yeah, we'll pick it up, or I'll pick it up later, and just study this by myself, and then we'll probably be into a different video next time I go streaming, and that's hopefully cool with you. But yeah, so thanks for coming along on this streaming accountability study, on this accountability study stream with me. My name is Aaron. I'm a data scientist, currently working in government. And I would love to hear what kind of data science stuff you're curious to learn, or if you're just using this accountability stream yourself as a way to keep yourself accountable. Like, what are you studying? Feel free to contact me. Any of my channels, you can see them listed here. For now, at least, we'll see about getting something new and making it a little bit more discrete in terms of which things are which. So yeah, it's good to study with you, and I hope to see you all again soon. All right, have a nice night. Bye.